Okay, sets. What is a set? A set is a collection of distinct objects. The objects inside the set are not necessarily to be ordered in some way, just distinct objects listed in some way. And these objects will be called elements or members of the set. And the set is said to contain its elements. And we will write a, small a belongs to capital A to denote that A is an element. Small a is an element of the set capital A. And we will write A does not belong to the capital A if A is not an element. So these are easy notations. We will use uppercase letters to denote sets, as we see here. This is capital V and capital O. And we may call this set to be capital S. And elements are usually, we use for elements lowercase letters. So the set V of all vowels in the English alphabet can be written as V equal A, E, I, O, U. So here we will write like the letter I belongs to V, but the letter D, for example, does not belong to V. This is what we mean by these notations above here. Same thing if we say the set of the set O of odd positive integers that are less than 10. So we are specifying, giving some property to the element. We want to be odd and positive and less than 10. And then these numbers are 1, 3, 5, 7, and 9. So we take them together and form a set, and we call it O. And here we will see that 3 belongs to O. Just we want to get used to these notations, but 4 does not belong to the set O, and so on. And this example, the set of positive integers less than 100. In here, this example is meant to explain to you that we will use dots this way to represent sets. So we will use these dots. It is does not make sense to list all the numbers from 1 to 100. We just write the first 2, 3 numbers and then 3 dots and then the last number. So this is one way to express sets. Okay. Now, usually in mathematics, sets are described in what we so-called set builder notation, which means the element of the sets will be characterized by some property or properties that they must have in order to be members of the set. For example, in general, we will write this notation here. A set is X, and this notation here, so I need some space to it. This notation here means such that. So we will have X, which X? The X such that X has the property P. So this is one way to write the notation. So and it is written here the set of all X such that X has this property. Okay, so for instance, if we want to say we want to list all the odd positive integers that are less than 100. There are 50 of them in there, 49. So we will not write them explicitly one element by another. We will use this notation, and we will say the set X, the set O consists of all element X such that X is an odd positive integer less than 100, and simply we will say X belongs to Z plus. What is Z plus here? We mean all the positive integers, but we will not take all of them. We will just say X is odd, so this is first property, and X is less than 10 here. Sorry, I said 100. It could be 100 as another example. Okay, and also we can use this way to describe the set of all positive rational numbers, and we will say this set. The set of positive rational numbers consists of real numbers, x belongs to R here means the real numbers, such that x equals p over q for some positive integers b and q. So any positive rational number can be presented as p over q, where p and q are integers. And here it is enough to say positive integers. If you want to say, okay, what's about negative 2 over negative 3, why would not take it? It is the same as 2 over 3. So it is enough to say the denominator below and the numerator above are positive. Okay, so this is the way to build sets. And we need to learn about the sets that we will use frequently in this course. We want to agree on these sets. The sets of natural numbers, this is n. The natural numbers 0, 1, 2, 3, 4, 5, and so on. So they are integers, non-negative integer. When we say non-negative, it means positive or 0. And they are called the set of natural numbers, and it is written in bold N. But we will write it this way. There will be 2 lines here, 2 lines. This is the set of natural numbers. Some people, some books adopt that the 0 is not natural numbers. So if you might find another book where the set of natural numbers are consist of 1, 2, 3, 4, not having the 0. I myself agree that 0 is not a natural number, but we will go with the book. Z is the set of integers, all integers, positive, negative, and the 0. So the set of all integers, and we will adopt this notation for it. Z plus, the set of positive integers. So when we say plus here, so we mean the set of positive integers. Q, the set of rational numbers, p over q, where p is in z, q is in z, but the denominator is not 0. So this is the set of rational numbers, and we will denote it like this, q. The set of real numbers, all the numbers you know, assuming you don't know yet the complex numbers. And when we want to take the set of positive real numbers, we just add positive on top of r. And the set of complex number, if you don't know what this means, don't worry about. It depends actually in the imaginary number, which is we call I is the square root of negative 1. So you don't have to worry about it for now. Other kinds, so we need to know these n, z, z plus, q, r plus. These notations are the same in all books of mathematics or other sciences. Okay, some other kind of sets are intervals. You have seen intervals before, either closed interval, and you know what that means. All numbers greater than or equal a, or less than or equal, and less than or equal b. And you know the open interval here means we will not take b. X is less than b, but x is greater than or equal b. And it is open from here, so we will not allow x to equal a. And it is open from both sides, so we will take all real numbers between x and a without taking x and b, without taking the a and the b. So we will not have equalities here. This is not equalities, this is just a Venn diagram. It is a way to represent sets. We will use the universal set, and we will denote it by a rectangle. What do we mean by universal set? The domain where we are taking elements from. We have just seen an example before that we were assuming ourselves taking the elements from positive integers. And another time we were assuming that we take any x from positive real numbers. So at the first case, my universal set was the positive integers. In the second case, it was the positive real numbers. So we will denote it by a rectangle, and the following. This rectangle will means all the universal set all the domain where I take all x from. I may say, okay, this is some set B, and then I may say, okay, inside some set B there is another set which is called A, and I can see here A lives inside B, and I can say here there is an element here which is inside B, not inside A. This is Venn diagrams. Or we will say, okay, we have just seen a set which was we called O, a set O, which consists of odd integers less than 10. So we will say, okay, this is 1, this is 3, this is 5, this is 7, and this is 9. Just this is a demonstration. So this letter is O, is not a circle. This is a demonstration, some demonstration of the sets. We will use dots to represent elements, and circles or some closed shapes to represent sets, and the rectangle to represent the universal set. So all this thing is called Venn diagram. Okay. It is possible that a set is contained in some other sets. In this case, we will say set A is a subset of a set B, and it is written this way. When is that possible? If and only if every element of A is also an element of B. Okay, so in here it says when we have A is contained or equal in B, if and only if the quantification, this quantification says for every x, if x is in A, then x must be in B. So this quantification for every x must be true. So this is writing the meaning of subset using quantifiers. Okay, and to test that A is a subset of B, which means to show that A is contained in B. So we show that if x belongs to A, then x belongs to B. Okay, and to show that A is not a subset, and it is written in this way, we need to find some element in A, but it is not in B. And to write that here, let us make a Venn diagram to understand this situation. So this is the universal set. So to show that A is not contained in B, assume this is the set B, and so that A does not contain in B, there must be an element which is not in B, but that element is in A. So we may have A to share some elements with B or not. This is A, but now we have this element here. This element here, if we call it X, then this X belongs to A, but it does not belong to B, and that is enough to show that A is not contained in B. Okay, and we may call that X a counterexample. Okay, and if you go back here, we'll say B is a superset of A. This is very, very rarely used. Okay, now we have seen a subset, but sometimes we use proper subset, which means here A is contained in B, but A will never equals B. It is strictly contained, and then we will call it proper subset. Whenever A is a subset of B, but A does not equal B. And that means if we want to write it using quantifiers, A is contained in B if and only for every x, if x is in A, then x is in B. That means A is a subset of B, but we want to add some other part which indicates that it is a proper subset. And then we say there exists element in P, there exists x which is an element of P, and it is not an element of A. And it is not an element of A. To make that clear, let's make a Venn diagram for a proper subset. If this is the universal set, then, and this is the set B, and this is the set A, then for A to be proper subset of B, we must have some X here. Now you see X is inside B, and X is not inside A. So X belongs to B, but X does not belong to A. And the whole of A is contained inside B. Okay. Now a definition, this says whenever two sets are equal, we will say two sets are equal if they have the same elements. That means A and B are equal if and only if this quantifier is true for every x. If x is in A, then x is in B. And the opposite, if x is in B, then x is in A. That means A is a subset of B and B is a subset of A. And here we go. A is a subset of B and B is a subset of A. So to prove two sets are equal, we will go this way. And we will need that later. For example, if you look at this set 1, 3, 5, it is the same as 3, 5, 1. At the beginning, we said the set is an unordered collection of elements. So the order of elements inside the set does not matter. And also, the repetition will not matter. We will just keep looking at this set as this in here. And if we call this to be the set S, we will write in a little while that the numbers of the set of the elements, of the distinct elements, when we write that, we will call it cardinality in a little while, which means the number of the distinct element inside the set consists only of 3 elements. So this repetition did not increase the cardinality. And in here we have an example how we for two sets that are equal but not explicitly stated to be equal. If we take this set to be the empty set, singleton set A, singleton set B, and the set containing A, B, and if we take the set B to be all X such that X is a subset of A, B. So we want to see all subsets of AB, and there will be phi. Phi is always a subset of any other set, and singleton set A, singleton set B, and AB itself. And then these two sets, they are equal. We just here note that as set C, we will write this. It belongs. So A as singleton element does not belong to capital A, small a, because it is not here. Look at it here. We don't see an element A living itself by there. But we will see A with braces as a set lives inside capital A. And in a theorem, this is trivial but very commonly used. Phi is always a subset of any set. Phi is always a subset of any set, and any set is a subset of itself. Okay. Size of the set means the number of elements inside that set whenever we can count them, when it is finite. So if S is a set and it has exactly n distinct, so we will count the distinct elements, and then we will say this S is finite and the cardinality of S is equals to n, and it is denoted this way, and we will write this equals to n. So this is the cardinality of S, the number of distinct elements inside S. So if we take A to be the set of odd positive integers less than 10, they are 1, 3, 5, 7, and 9. So we have 5 elements. And if we take the set of letters in the English alphabet, we know there are 26 letters. and the null set, the empty set, has no element. So the cardinality of the null set is 0. It contains 0 element. A set is said to be infinite if it is not finite. So example of infinite set, simply the integers. It is an infinite set. The positive integers, the real numbers, the rational numbers, all sets we have already seen of this kind are infinite sets. The set of even integers, the set of positive integers. There are many infinite sets. Another example of infinite sets, any interval is an infinite set because it contains all the real numbers inside that interval, either open or closed from one side and so on. Every one of them is an infinite set. Okay. Now, power set. So what we learn in this lecture, just the definition to get used to some terminology. All combinations of elements of a set is called power set. Assume we have a set that has elements inside it, finitely many. So all combination means I will take like 3 elements. So all possible 3 elements that I can choose. What are they? Or I will say I will take only 2 elements. So I have too many choices for 2 elements. Or just 1 element. So have a the same as number of elements in the S as choices for such a thing. So these are called combinations. Either take no element, or take 1 element, or take subset consisting of 1 element, or 2 elements, or 3 elements, or 4 elements from the elements of the set. All these combinations together, combination of subsets, will be defined as a power set of Sn, and there is a reason to call it power set, and we will see. And is denoted this way, assuming we have the set to be 0, 1, 2. So all combinations will be the phi, which means I take nothing. Or I will take subset, each consists of 1 element, singleton subset. That will be either 0 alone, the 1 alone, the 2 alone. Or I will take combinations of 2 elements. So I will take 0, 1, 0, 2, 1, 2. Okay, or I will take the combination of all 3 elements, the whole element of the set, and then this set come out. And if you notice that in the power set, the set itself will live in the power set, and the empty set will be in the power set. I mean here, as a set, it is always an element of the power set of itself, and also the empty set is an element of that set, and this applies for any set S. Now here says if S has n elements, then the power set will have 2 to power n elements, 2 to power n of subsets, and we will know later, we will learn why this is true. Like in here, if this set is S, then it has 3 elements. The number of S is 3 elements, and this is n. In here, we means the empty set is okay. This one is n. So the power set of S will consist 2 times 3, and that equals 8 elements, and we count them 1, 2, 3, 4, 5, 6, 7, 8 elements. Okay, so this is a quick look at the power set. Here we will introduce Cartesian products. Like if we have sets, we can make new sets out of them. Let's see. To know that, let's first introduce what we mean by this. This is a generalization of ordered pair. Ordered pair used to see A or AB, or we will say here A1, A2. This is ordered pair, and usually this is denoted for the x coordinate, and this is the y coordinate. These are ordered paired. Now we will have ordered n-tuple. It has n components. Generalization of ordered pair, but it has n components. Is the ordered collection of A1 comes from A1 is in the set in the coordinate, first coordinate, second coordinate is A2, and so on, and nth in the nth coordinate. Now to have 2 n-tuple ordered and tuple to be equal, we must have that corresponding coordinates to be the same, which means first coordinate here must equal first coordinate here, second must equal the second one, and so on till we reach the last one. And this is written that AI equals BI for every I from 1 to n. Now, this is the n tuple. We needed to define the Cartesian product of sets. Now, we will define the Cartesian product. If we have two sets A and B, if we have two sets A and B, then the Cartesian product of A and B is A cross B. So we are saying here the Cartesian product of A, we're mentioning A first, and B, then we're mentioning B second, and we put A first here and B second. And it consists of ordered pairs where this comes from the set capital A and this comes from the set capital B, and it is written here A belongs to capital A and B belongs to capital B. And here is an example. If A is E12 and B is ABC, then we will make ordered pairs so that the first coordinate are the elements is from the element of A. So we have 1. So we have 3 ordered pairs that contains 1 in first coordinate. That's because we have 3 elements in B. So 1 with A, 1 with B, 1 with C. And then we go to the second element of A. 2 with A, 2 with B, 2 with C. Now, if we write B cross A, then the places will be swapped. So we will have A1, A2, A3, A1, A2. Sorry, we'll have A1, A2, B1, B2, and C1, C3. So the first coordinate here will contain elements that comes from that comes first. Okay, and you notice here A cross B is not equal to B cross A. That when we change the coordinate, we change the order. But there are some cases where A cross B equals A. One case is one of the sets to be empty. That's because if one of the sets is empty, then the cross product is empty. I mean here, phi. This is the empty set. Cross any set, we will just have phi. Or any set cross phi, again we will have empty set. So and the other case where A cross B is B cross A, if it is whenever A and B are the same set, so it does not matter the change of the places of elements because they come from the same set. And now we can generalize this cross product to not only to sets, but we can use as many sets as we want. So the cross product of the sets A1, A2, AN, and it is denoted this way. Here we go. It consists of n tuples such that AI is an element of the capital AI. So this is from the set that comes here first, and in the second coordinate the elements that are from the set in the second place, and so on. An example of that, if A is 0, 1, B is 1, 2, and C is 0, 1, 2, then A cross B cross C is that. And you need to play with that so that you see we will have here we have 0 and then we have 1. So the 0 will take all the possibilities. So it will have how many possibilities in there? 6 possibilities. Because when you have first place 0, then second place will be either this or this. For any of these choices, in here, you will have 3 choices. For any of these choices, you will have 3 choices. 3 choices for this, 3 choices for that, and you can guess now. So again, for one choice here, let me use another color. For one choice here, you have 2 choices here, and each one choice here has 3 choices. Okay, so but we have 2 elements here, so we'll have how many elements? 2 times 2 times 3. 2 times 2 times 3. Can we guess that? Here I'm guessing that the number of elements here is the same as the number of elements in A times, these are numbers, number of elements in B times number of elements of C. Can we generalize that? So I will let it for you to think about. And same thing here, we can use notation. A square means A cross A to power 3 means A cross A cross A, and so on. A to power n means A cross A n times, which means n tuple. It is the set that consists of n tuples, and the coordinates are all from the same set. Okay, and an example actually of this here is what you use to deal with, which is R square. That consists of n ordered pairs such that A, B are from R, and this is simply the XY plane. The XY plane that you use to work in. Okay, now this is an example here. It just says if A equals 1, 2, then A square. I will let you have fun to compute that. Now we come to the relations here. It is a quick introduction to relation. We will learn a section about that. A relation is simply a subset, call it R, of the Cartesian product A cross B. It is called a relation. Now we have set A and set B. A cross B, which means a lot of ordered pairs, okay, connecting elements from A to elements from B. Now, if I want to define a relation between elements of A and elements of B, I can say, oh, okay, I want to choose this ordered pair. That means first coordinate is related to the second coordinate, put it here. Choose another one, put it here. Choose another one, put it here. So the ordered pairs I already chose define a relation between first coordinate and second coordinate. Some element might be chosen and some are not from sets A and B. That's okay. Let's see an example to understand that. If A is the set R consists of A0, A1, A3, B1, B2, C0, and C3, where we are taking these sets from, and we are assuming A here. Actually, it is written here. A is this set. This is A, and this is B. Now, look here. A cross B consists of many elements. Like I will say, the cardinality of A cross B has 3 times 4, 12 elements. But here in this relation, we're choosing 6 of them. 1, 2, 3, 4, 6 of them, not all of them. So the ordered pair we chose decide the relation. In here, we are saying, the elements from A, which is small a, relates to 0, and A relates to 1 again, and A relates to 3. But A is not related to 2. A is not related to 2 because this ordered pair does not belong to R, the relation we are defining. And here we are saying B is related to 1, B is related to 2, and so B is not related to 3 because this ordered pair has not been chosen. And same thing for C. Okay. Here is another relation. What are the ordered pair in less than or equal to the relation whenever... Okay, so we have this set 0, 1, 2, and 3. It says define a relation between two elements. Write it this way, A, comma B. It is an ordered pair. And don't write it this way unless A is less than or equal B. This is the relation between A and B. So now, if we write this to be capital A, then A cross A will have so many elements. For example, I will write here like 3, 2, this belongs to A cross A, but it does not belong to the relation we are defining, because 3 is not less than or equal to. So we will not choose this ordered pair as in our relation. So the relation will consist of all elements of A cross A such that they are ordered pairs, such that first coordinate is less than or equal second coordinate. So surely 0 will be chosen with 0, and with 1, and with 2, and with 3. But we will not choose 1 and 0. We will choose 1 and 1, 1 and 2, 1 and 3. Say 1 and 0 is not in R. Indeed, because 1 is not less than or equal 0. And here 2 and 2, 2 and 3, and 2 and 1 is not in R. And here 3 and 3, simply because 3, 1, 3, 2, or 3, 0, any one of them is not in R. So again, a relation is a subset of A cross B, relation between A and B, or a relation on A itself is a subset of A cross A. Okay. And now using set notation with the quantifier, we will need that kind of notation. It says here, this notation means the following: for every x, if x is from the set S, then this property must happen. For every x in the set S, P of x happen. We want to write it somewhere. Again, for every element x in the set S, a property P of x happen. So we will write it this way: for every x, S of P of x. That means every element of S will satisfy the property P of x. Here it means there exists an element in S. There exists an element in S such that that element satisfies the property. And we will use the conjunction for this end. So there exists an element, x belong to us, and P of x happen, x satisfy that property. So we will write it this way: there exists an element x in S which satisfy the property. So we need to use to that. In here says, for every element in the real numbers, x squared is greater than 0. Is that correct or no? Every real number is greater than 0. So this says every element, for every element, or let me say it's a real number. So I will just say for every real number, for every real number x, we have x squared to be non-negative. It's greater than or equal 0. And this says there exists an integer, there exists an element from Z such that this happens. And this is true, right? Because 1 squared is 1. And the red means there exists an integer or some integers. Here we say integer x such that x squared equals 1, and we know x might be 1 or x negative 1, so there exists such an element. Okay, so this brings us to the end of this lecture. Okay. Thank you.